To organise the conference and conferences in the past, but she's also saved this presentation, so thank you, Tracy. So, ladies and gentlemen, we live in a new age where technology is revolutionising the world. Today, for the first time, you can step out into the road, be run over by a bus, whilst looking at your phone, checking for a bus timetable. You're a tough crowd. Okay, so this presentation is about a paper I wrote for JavaWorld. If you are interested in that paper, you can go to that little URI and have a read of it. It's been out for a while, so it's not kind of cutting edge or anything like that. In fact, it's just real world, getting to grips with OSGi, and follows on from some of Lars Vogel's examples. So I'm from Diamond Light Source, which is a particle accelerator, and I'm going to show you a little bit about. I've got some videos, and we're going to have kind of 10 minutes of what actually Diamond is, just for fun. But as an organisation, we're part of the Science Working Group, which is a collection of different Eclipse open source projects, and we use most of them. I think there's a few people from Science Working Group. Can you put your hands up? So yeah, there's quite a few, but if you want to join, science.eclipse.org. So I work at a particle accelerator, and when I'm not modelling the top right-hand corner, I work as a computer scientist. The synchrotron itself, I'm going to sort of talk about a bit about how it works. What it does in terms of science, actually, why do we build such a great big particle accelerator? That's because we want to look at different things in nature, different structures of materials. We look at the structure of the internal elements within the Earth. We do all sorts of other research into foods and pollution and metals moving through the environment. We look at the efficiency of solar panels, and probably about half the users are solving proteins at Diamond, so they're looking at trying to figure out the structure of organic molecules. And that's phenomenally useful, because actually organic molecules inside a cell are acting like very molecular level machines, and once they've built up all of those shapes, they can actually figure out how the machine works. And they actually make videos. Once they've built up all the shapes of the molecules, they actually show you this molecular machine churning out proteins and things, and it's very, very cool. So that's what Diamond does. So a quick video on how the machine works. So this is the building. It's just outside Oxford, which is roughly 70 miles from London. That's around 40, 50 kilometers. Oh no, it isn't. It's the other way around. It's 160. So there's an electron gun over at the start of the synchrotron, and that produces charge which streams away into a linear accelerator, and then electromagnetic radiation adds to the energy of those electrons in a booster ring. And they're put into a storage ring, and once they're in the storage ring, they're just going round giving off light. It looks circular there, but that's not the case. It's actually 48 straight sides. And at each corner and along each straight section, you have the ability to put an insertion device or a bending magnet, and either of those things can produce a beam, so a beam of light, so that you can imagine these electrons going around and there's lots of beams of light coming out. Inside an experiment, so this is, it says at the bottom, this is a diffraction beamline. And the light, this is light now, not electrons. We're done with the electrons, this is light. It's being reflected off some mirrors, goes through some slits, and then it hits a crystal, which is looking like a diamond, because it doesn't really look like that when you crystallize proteins. It's a tiny little thing that you can hardly see. Produces a spot pattern, and that pattern, in the case of crystallography, you can use to work back the structure, because basically your light is such high energy that it's on the same scale as the lattice of the crystal. So as it goes through, you get diffraction patterns, and those are what those spots are. And you can work backwards from those spots to figure out the structure of the protein. So this is a robot arm. Now the scientist who's in charge of this arm reliably informs me that it's much faster today, and this is a slow video, Anyway, it's good enough. So what it's doing is taking a crystal sample. So this is actually the real kit of that diagram we just saw. And it takes a crystal sample out of the dewar, which is a cooled area, because these crystals are normally kept very cold. And they're put into the beam, and that thing on the left-hand side, which rotates the crystals, called a goniometer. The beam's coming through that, where that robot is now, and not yet, only when the shutter's open. And the blue thing in the top, very far left-hand corner is a detector, and that writes files, which are basically the data. So obviously we don't use photographic plate in the modern age. We use detectors and file systems. And nowadays they're kind of 16 megapixels, 100 hertz. So they're, you've got this massive volume of data, which before you didn't have. So onto the software. So I've been kind of hacking away at GDA and other products at Diamond for about 9 years now. There's 3 million lines of code roughly, and before we moved to OSGi, the server was a big static class path. As well as the server, we had a thick Java client written in RCP, which basically, I should probably make clear, when the light comes out of the machine, you don't want to be stood in the way, right? It's X-rays, so it's not really light, it's high energy electromagnetic radiation. So you don't want to stand in the way. So everything we do is robots. That's why we have the robot arm. That's why we have the mirrors and everything is. So we just look at it through a piece of glass, right? And we have a computer screen and we have an RCP application to control it. Our product, as it was, which I'm going to actually highlight some of the problems with it, which are many and varied, was a legacy system, and it came from a previous synchrotron. And one of the problems we had actually was a run from source culture. So basically each beamline was just saying, here's some source code, put it over here, massage it a bit, change a few lines of code, do a bit of configuration, end up with a product. So every beamline had a bespoke product. So this is not a reproducible software system. And that was the issue that OSGi helped us solve. And the other problem was that over the time, obviously, we had all these lines of code. We kept adding to them. We had no real structure around it. It was just each beamline had a whole bunch of code. And the proportion of novel software development needed to increase, because the rate of technology, the detectors are getting faster, the motors are getting faster, the file systems need to keep up. We have to do more development as a proportion of our time just to keep up with the changes in the beamline, which is quite and of course you could imagine with all that code, we're doing the opposite, right? the cost of support and the lack of process around it, and the lack of control and reproducibility is basically, our cost of support is going up, not down. So we had to do something about it. Some of the problems we had are different APIs that do similar things, overly interconnected projects and classes, improper encapsulation, poor unit tests, and it's almost impossible to coordinate any kind of development. So OSGi has helped us with this, and I'll going to get on in a minute to 7 kind of ways in which it's helped us. But first I want to say some of the motivations. So we really wanted to move to a better mapping system. And what mapping is, funnily enough, you can't move the beam, right? It's a machine of almost 1 kilometer in diameter. So once the beam comes out of the machine, you don't really want to be moving it, right? So you move the sample. And so if you want to scan across a two-dimensional thing and build up information, maybe you're looking at spectroscopy or whatever, you need to move the sample around on a plate. And basically, about a third of the beamlines, that's what they do. They're moving stuff around in the beam. So we had this idea of having a mapping project where we actually make a kind of mini product inside the main product, which is reproducibly built and can be the same on every beamline. So we had a kind of driver there that we had to get out a new kind of quite a big chunk of software. So I had a reason to go to the bosses and say, well, while we're at it, let's make sure we use an OSGi server for our back end. So that was the kind of driver which gave us an excuse to change the way the server worked. This project really is kind of soup to nuts, as the Americans say. So you have to, you basically want to come into the synchrotron with a sample, and you want to define some analysis and then run, and it'll just run the whole thing for you. So you'll just do the whole map as fast as possible, write a file, run your analysis, which you've defined before you've started your experiment, and get your result back in real time. So this normally you just give them a bunch of files and they go away and come back in, you know, in a few months and say we need to do another experiment because we didn't do it right the first time. So they got really excited when they did the first prototype, and I think you'll probably be riveted by this. This is the sample stage moving around, and the beam is signifying the is modelled by a pen. But anyway, so we can move some motors. Yeah, thank you. I just thought it's interesting to see where we were 2 years ago. So that's 1.5, 2 years ago. So we've moved on quite a bit. This is another early prototype from about the same time. So we have a lab where we get to play with motors. So we get to run software with the motors before it goes on the beamline. And here that's the sample stage moving. Obviously on the real beamline it would be oriented differently and there'd be different hardware. But we're moving that around, and Tom here is showing off his new toy. So this is basically a mapping scan. It's quite interesting because like the sample is too small to really kind of align in any proper way. So you put it in the beam, then you try and figure out how you want to scan. So we're not talking about, we put it in the beam, we have a nice axis aligned scan. In fact, it's all different, you know, funny angles involved, and he has to do lots of calculations about getting the scan path right. So there's lots of 2D maths that he has to do. So I wanted to talk about the software architecture so you can understand where Java comes in. So at the motor end, we've got the embedded software. You've got PMAC drivers and other physical detectors, which have all got APIs that come with them. We drive those APIs through basically C++ code, which is linked into a control system called Epix. And we have PMAC drivers and input-output controllers, which are basically usually Linux machines. And those basically, you have a suite of motors whose embedded layer is integrated into a given PMAC. Maybe, you know, it could be 4 motors, say. And so you can address those motors and move them using the API. They also, if it's a physical device like a detector that can output data, they also do that at the low level, right? Because we want to, when we're writing does everyone know has anyone heard of HTF5 or not heard of HTF5? Not? All right, so there's 5 or 6. So this is if you've got loads of binary data, it's a way of putting that into a file and giving it a dimensionality and giving it a type. So you've got a bunch of floats in a big array that the detector's giving you, and then you write them, and it gives you a nice file format to read it, and you can slice it and you can do different things. So you can give it axes and give it properties. So it's a very nice, and it's very efficient, super fast file format for that. So the detector writes that HTF5 file. Where the Java comes in, it talks to something called Malcolm, which is a Python code, and using the protocol called Epix v4, which I think only about one person in the room is familiar with, but it's a protocol for driving devices. And the acquisition server is, as I say, it was a static class path. This talk is going to be about how we migrated it to OSGi. And then there's a front end, as I say, written in RCP. And you can see that Eclipse January features on our analysis, which is running on the cluster. It features in our user interface. It's a way of describing our data for slicing and dicing. We use Eclipse January also on the acquisition server. So it's a core technology that we've adopted from Eclipse. I haven't got much time left, have I? Is anyone not familiar with OSGi? Okay. Just one. So OSGi is a way of breaking up your class loading into so you don't have to, when you start your application, you don't have to load all of the application straight away. You load it incrementally. So it's called dynamic class loading. And the other thing you can do with it is you've got services, so you can get an instance of an interface from OSGi. Okay, so how did we make it into a OSGi server, and what problems did we hit? So the great thing about OSGi, of course, you can have loads and loads of code, but not all of it's loaded in memory until you use it. So that's really good for us. We've got 3 million lines, all these bundles We can make a server really easily. But we had this run from source culture. And that gives us a problem, because OSGi much prefers to have all these bundles that it can load in dynamically, and so it prefers a binary when it runs. So on the one hand, we need a binary to make OSGi work, but on the other hand, we were basically running from source on the beamline. So that's where JRebel stepped in. So it gives you the abilities. If people use JRebel, anyone in the room? Okay, that's less than I'd expect, actually. Okay, so it gives you the ability to, in a running OSGi container, among other things, it does other stuff, but in a running OSGi container, you can insert code, and you can leave it running with that code. So as you debug, if you change stuff, you can actually update that bundle onto that server without restarting the server, without rebuilding the server. So that, for us, gave us that live ability. So before we had all this source code, if something went wrong, we could just edit the source code, live, and then restart the application. With JRebel, it can be in the binary, but we can actually edit the binary live. So that was the first problem solved. We didn't need to run from source anymore, so we could have a product. The next problem was that we were using Spring like never before. Like all the motors, all the detectors are configured in Spring. So you've got this big Spring file, and it pulls in code from everywhere. It's not going to work with a static class path. And there's different ways, without a static class path, there's different ways of sort of dealing with OSGi and Spring. What we've chosen, and this may not be the best, but it worked for us, was we used Eclipse Buddy because we're using Equinox. So Eclipse Buddy is a specific way in Equinox of making connections between bundles. So there's different OSGi containers. One of them is Equinox, and that has a specific way of saying these bundles always get loaded. So if we have our big Spring file and all of the things that we want to load from Spring are in, I don't know, 20, 30 bundles, they're all kind of interconnected, and they're all loaded up using Eclipse Buddy as a big block, and then we can run Spring. So one of the things that was great was we made bundles, but in the past we had a kind of core. So we had a kind of core software that imported all of the other stuff and then did the experiment. And with OSGi, that's not really how you do it, right? You have services that are provided by different bundles. You consume those services, and in your central bit, you don't really need to make a lot of dependencies. You can just bring in the API bundle, which has low dependencies, and consume those services and use them. So we can't change that overnight. So what we're doing is making the code more modular, and basically, we've got to try and change the minds of the developers. We've got to try and make them work a new way, and to say, if you want a piece of functionality, make an interface for it, put the interface in a no dependency bundle, implement that in another bundle, import that interface as an OSGi service in your running code. Yeah, that's a bit to get their head around. That's different to how they used to do it. And so what we've found is I've managed to persuade some evangelists in different areas of the product, and they actually are willing to do it that way. And hopefully over time, we're going to just get people moving on. I guess we've got about 5 people now who are really into this stuff. So during this process, we had to rewrite the scanning algorithm because it basically, we'd gone to OSGi and we got all these services that we could consume. So for instance, we could say, give me the motor service, I want to move a motor. Give me the detector service, I want to move a detector. Give me the file writing service, I want to write a file. That's not how the old scanning worked, right? It just basically had loads of singleton patterns and pulled things in. And there was no real way we could have migrated that out and not broken something, or the unit tests were quite poor. So we took the decision to actually make another scanning system, like an OSGi one. And that was, we called that Solstice Scan, which is the nickname of our new server, and it does this mapping that it does this two-dimensional. Actually, it's n-dimensional. It doesn't really mind about the motor dimensions. So cardinality was another issue with OSGi services. Has anyone hit that? Has anyone come across cardinality? Yeah. So it's quite important to understand what they mean by it and get it right. So if you have one service and you only ever have one, you need to set that cardinality correct when you make the service. And you know, if there are multiple of them, you need to set it. And it's important to do that, or else funny things happen. So that was something we initially we went through all the code and said, there's either naught or one of them. But that's not ideal. You have to think about if it must be there, it must be there, and the OSGi will then figure out what has to be loaded. So we did have this issue with Declarative Services, which is where we're pulling in these services, in that after a while, when you get like, okay, you've got 3 of them, it's not such a problem. When you have 33 or when you have 99, it's it suddenly becomes that you get random messages. And not only that, but we actually had different configurations going on. We had different things we were pulling in, and then something wouldn't be there for one of the services, and you get this, I cannot start this service error. And it's very difficult to find out how, you know, how to solve those problems. Sometimes the code just works, and you get lots of error messages, and then everything's fine. And other times it's not working, and that's the only message you get. So we set this system property Equinox DS print, which helped, and as I say, we got the cardinality right, which helped. And that's still an issue today. We still have lots and lots of messages in certain configurations that pop up, and we have to figure out where those services have gone. And the final point I'd like to make is the hidden cost of test-driven development, because we moved all of these classes from singletons to nice, you know, concrete classes to nice OSGi services. So what did we do? We basically made a bunch of unit tests to test all these services. After all, we just made a new service, so we wanted to test it. And then suddenly our build system was taking kind of 45 minutes or an hour to run, and we have a submit queue, right? So a developer cannot check in code until they pass the unit test and they pass the review. And so this was slowing everything up. And how we solved that was we've basically broken up our server into a few different projects. Some of them are in-house, and some of them are on GitHub, some of them are Eclipse projects, some of them are just on GitHub under the Diamond Light Source account. And each of those has a Travis build separate, and it's like a module with some tests. And in that way, we've broken up the build so that a given developer, okay, they can break the API, so we still have a complete build, but all of the modules have their own builds. So this sort of solved the problem. So if you're editing a module now, you can kind of get away with 10 minutes or so on the build and test cycle before you can check stuff in. And then obviously, after you do that, you're going to get a main build happen. You may have broken the API, but actually that's such a theoretical risk. It's not. In reality, most developers know, you know, if they're hitting an interface, there's probably code that calls that. I'll go and check. But if they don't check, we will get a build. That maybe happens, I don't know, once every 2 months or something. And that's quite a few check-ins. So I may have a video of stuff happening. So you can, just to give you an idea of the mapping project. So in the GUI, this is a spiral pattern. So it's going, and it's moving the sample around in the beam, and the data is being written to a file, and then that file is being visualized back in this RCP GUI. This is actually a different GUI. If you went, for the people in the science working group, I did a demo of this on Monday. This is a different GUI running the same scanning algorithm. So this is not in the scanning project. So we've built multiple GUIs on top of the scanning stuff. And this is the results of a pipeline. So as we're doing this map, the results are coming back, and actually you can see it's a Mandelbrot set. So it's just an in-memory detector. Okay. I'm going to hit straight to conclusions because we're running short of time. So OSGi has made our code modular, broken it up just as it promised it would, and it's made our server start up faster. It's given us standard tools. It's a very mature and easy to use system. We were just using basic tools that come with it come with Eclipse. I believe the bind tools are even better, but we haven't tried those yet. But it's very, as I say, there's lots of blogs. It's very easy to do. It gave us an opportunity to increase tests because we're making everything modular. We tested all the modules, and we even added a few new features like a new scanning algorithm. Okay, thank you very much.